Solubility Equilibria. So we learned about solubility rules back in chapter 4 in 1A, and that allows us to calculate classify ionic compounds qualitatively as being soluble or insoluble. Now we can look at degrees of solubility, because just like with wealth and people, a rich person, a poor person, those terms are relative, right? And there's no dividing line directly in the middle. It's a continuum, it's not a quantized thing. So there are degrees of solubility. So we can look at dissolution as an equilibrium. So here we're looking at the example of calcium fluoride. So this solid will dissolve in water and it will make calcium ions and 2 fluoride ions. These will be aqueous because they're dissolved in the water. This is a solid. So we can calculate an equilibrium constant for this chemical reaction. So the equilibrium constant will equal the concentrations, of the products divided by the concentrations of the reactants. The reactant is a solid. Solids don't change their concentrations, so we've left them out of equilibrium constant expression. So we've got calcium ion times fluoride ion squared. So that's the equilibrium constant for this equation. Because this is something dissolving, we give this one a special name. It's KSP. It's the solubility product constant, because we're talking about solubility. So we've got Ka, we've got Kb, and now we've got KSP. So solubility is the amount or the quantity of compound that dissolves in a certain amount of liquid, and this can be measured with different units. Sometimes it's measured as the mass that will dissolve in 100 milliliters of water. Here we're going to be looking mostly at molar solubility. So molar solubility is solubility in units of moles per liter. So we're looking at the moles of the substance that will dissolve per liter of solution. We can calculate that from the KSP. It's important to note that KSP is not the molar solubility. Molar solubility can vary depending on common ions or pH of the solution. KSP is a constant at a given temperature. It will change with the temperature change, but otherwise it's a constant. So to find molar solubility, we're going to do equilibrium calculations. So this should be just a variation on a theme. Let's look at silver chloride. So here's silver chloride. Its solubility product constant is 1.77 times 10 to the minus 10, which is quite small. From our study of solubility rules, I would expect you to tell me that silver chloride is insoluble. So great, now I've got my little, oh good, it went away. Did you see that white square? I don't know why that shows up. So we can write an equation for the solubility, or the dissolving of silver chloride. So we get silver ion and chloride ion. We can write an expression for that. So KSP is going to equal the silver ion concentration times the chloride ion concentration. So when we initially start this, we put solid into the water and there's no silver ion and there's no chloride ion. As this dissolves, we're going to have an increase or a change in the concentration for each of these. Here, instead of calling this X, we call it S. S is the molar solubility. So this is going to change by plus S, that's going to change by plus S. And at equilibrium, the concentrations of each of these should be S. So we can say that KSP then is equal to S squared, right? So the molar solubility is equal to the square root of KSP, the square root of 1.77 times 10 to the minus 10. .33 times 10 to the minus 5. And the concentration is going to be molar. So in decimal form, is that a significant concentration? For most purposes, no. You can't make a 0.01 molar solution of silver chloride because it won't dissolve. Is it absolutely insoluble? No. A little bit dissolves, but it's not enough to be significant most of the time. Any questions? KSPs, you look them up in a book. As you're doing worksheets and things and you need to look up equilibrium constants, I was grading worksheet 16. I don't know where some of you got your KAs and your KBs, but I couldn't find those on the internet. Not the ones you gave me. Everything you need should be in the appendix in the back of your textbook. On an exam, I'll give you either these tables that you can look it up, or I'll just hand you the value in the problem. So let's calculate the molar solubility for iron 2 hydroxide in pure water, and the KSP is 4.87 times 10 to the minus 17th. So not very soluble. The first thing we should do is to write an equation, a chemical equation, showing how this dissolves. So we've got iron, FeOH2 solid. Okay, so let's see if I can find, no, I lost my writing, but make it over again. Okay. So we're writing the equation for this dissolving. So we're going to get iron 2 ion and 2 hydroxide ions. You know that from the formula. So we can use that equation to make our ice table. Initially we've got 0 of the iron ion and 0 of the hydroxide ion. The change will be plus S for the iron, and what for the hydroxide? Plus 2S. Don't forget the stoichiometry there. So then at equilibrium, we've got S and we've got 2S. I'm putting serifs on my 2's because otherwise they look like 5's. So KSP equals Fe2 ion concentration times hydroxide ion concentration squared, right? So I've got the KSP value, 4.87 times 10 to the minus 17, and that's going to equal S times the quantity 2S squared, which is 4S cubed, right? So then S is going to equal, we're going to take the KSP and divide by that 4 and then take the cube root of that whole thing. Your calculator should have a way of doing cube root. Yeah, I'll tell you. On the TI-36X Pro, what you're going to do is you're going to press the 3 because you want the cube root button. Then you're going to press second, and it's just above the square root. It looks like a square with a little box. The 3 is what goes in the box. So now it's flashing with the cursor, and now I'm gonna type in this part underneath. 4.87 times 10 to the minus 17th divided by 4 equals. And I'm getting that. 2.3 times 10 to the minus 6 molar. That's the solubility of iron 2 hydroxide. Any questions? The molar solubility of silver bromide in pure water is 7.3 times 10 to the minus 7th molar. Calculate KSP. So this is doing that backwards, right? So again, we should write the chemical equation for this dissolving, because we want to be clear that we've got the correct stoichiometry. We're given the molar solubility. So I'm still going to look at this ice table where I'm starting with 0 for both of those, and then there's 1 silver ion, so it's increasing by plus S. There's 1 bromide, so that's also plus S. So at equilibrium, we've got S and S. KSP is equal then to S squared, right? Silver ion concentration times bromide ion concentration. So I was given S, the molar solubility, so the KSP is going to be that number squared. Five 5.3 times 10 to the minus 13. Any questions? So the molar solubility and the KSP are related, but you can't just use them interchangeably, and you can't compare solubility necessarily by comparing KSP, because the stoichiometry has an effect, right? So here we're looking at magnesium hydroxide and iron carbonate. Iron carbonate, when it dissolves, it makes 2 ions, and when magnesium hydroxide dissolves, it makes 3 ions. So the equilibrium expression for this is magnesium times hydroxide squared. It's going to end up being S cubed, and this is going to be S squared. So we can look at their KSP values. Magnesium hydroxide has a lower KSP, but it has a higher solubility. Here we're looking at magnesium hydroxide and calcium fluoride. The stoichiometry is the same. We compare, this has a smaller KSP, larger KSP, smaller solubility, larger solubility. We can compare those two because the stoichiometry is the same. But if the stoichiometry is different, it's not necessarily going to be the same order.